Let's look at some application examples involving vectors. In this first example, we have a cruise ship that leaves Miami and travels 40 miles per hour in the direction of south 35 degrees east towards the Bahamas. The ocean current is moving north 10 degrees east at a speed of 8 miles per hour. Our goal is to figure out the velocity of the ship, because the water is going to affect the direction of the ship. To do that, we want to first express the velocity of the ship and the velocity of the ocean current as vectors, and then we can combine those two vectors together to figure out what the true velocity of the ship is going to be. So that's the velocity of the ship combined with the velocity of the ocean current. So let's start by looking at the velocity of the ship. Okay, so usually when we see the word velocity in a math and kind of science context, usually velocity is going to be, we're going to think of velocity as a vector, whereas speed would be the magnitude. So speed tells me how fast I'm going, velocity tells me the speed, but also direction. Okay, so our cruise ship, we are starting in Miami, and so I'm just going to draw sort of a little X and Y axis, and our cruise ship is going to start at the origin, and it's going to travel south 35 degrees east. Okay, so from the origin, southeast would be into an arrow or a ray or a vector into the fourth quadrant, and it's 35 degrees east of south. So I know the angle between our vector and the negative y-axis is 35 degrees. Okay, and we know the magnitude of this velocity vector. I'll use v for speed. V is our velocity of our ship. We know it is 40 miles per hour. Okay, so if I want to express that using a vector, right, we know that a vector can be expressed as the magnitude of the vector times the cosine of its direction angle. That's the horizontal component, and then the vertical component would be the magnitude of the vector times the sine of the angle. Okay, so we know what the magnitude is, it's 40 miles per hour, but we don't know the angle. Okay, we know the bearing or the heading angle is 35 degrees southeast, but I need to find the angle in terms of standard position. So standard position is starting at the positive x-axis and rotating around. And so if I rotated from the positive x-axis counterclockwise all the way to the negative y-axis, that's 270 degrees. And I'm going to continue rotating into the fourth quadrant by 35 degrees. Okay, so 270 plus 35 degrees is going to be 305 degrees. So that's actually the angle that I want to use when I compute my vector. So my velocity of the ship is going to be 40 times the cosine of 305 degrees. That's the x component, and then the y component is going to be 40 times the sine of 305 degrees. And if we use a calculator, we can compute that to be 22.94 in the horizontal component, and then a negative 32.77 in the vertical component. Okay, now we need to do the same thing for the wind. Sorry, for the ocean current. So let's kind of draw the same picture here. This time we know that the ocean current is traveling north 10 degrees east. So north is the positive y-axis and 10 degrees east. So from the positive y-axis, we're going to rotate counterclockwise 10 degrees. And that's north and that's east. So I'll use W for the water, for our ocean current here, we know that the magnitude of the ocean current is only 8 miles per hour. Okay, so the vector of the water, the ocean current, is going to be the same kind of setup. So it's going to be the magnitude of the ocean current times the cosine of theta, and then it's going to be the magnitude of W times the sine of theta. We already know the magnitude, we need to find theta. Well, I know it's in the first quadrant, this vector's in the first quadrant, and it's 10 degrees off, 10 degrees away from the positive y-axis. And so that means the standard position angle would only be 80 degrees. So theta has to be 80 degrees. Remember, we always need to have our angle for sine and cosine. Theta always must be a standard position angle. So my ocean current is going to be 8 times the cosine of 80 degrees for the horizontal, and then 8 times the sine of 80 degrees for the vertical component. And if we compute that using our calculator, we'll get a horizontal component of 1.39 and a vertical component of 7.88. Okay, now just to make kind of a quick glance at both of these, if we have a vector pointing southeast, that means the horizontal component should be positive and the vertical component should be negative. All right, and that's what we see for the ship, right? It's got a positive horizontal component and a negative vertical component. And then for the water current, it's pointing northeast into the first quadrant, so we should see a positive x and a positive y, a positive horizontal component and a positive vertical component. And we do see that happening in our vector. Okay, so we've done kind of the first part here. We figured out the velocity of the ship and of the current as vectors. So now we want to combine those together, okay? Because what's going to happen is the ship is traveling southeast, but the water current is going northeast. And so the water current is going to push the ship as it's traveling, and it's going to push it in the northeast direction. And so we're thinking of taking the velocity vector of the ship and adding it to the velocity vector of our ocean current, right? And so we've seen when we do an addition of two vectors, we take the second vector and put it at the arrowhead. That's where our initial point is going to be for our second vector. And then to find the resulting vector, we're going to start at the origin and draw the vector out to the final arrowhead, okay? So this it's still probably going to be in the fourth quadrant, but this is vector v plus vector w. Okay, so if we actually want to compute that, and this is part C here of our question, we want to look at v plus w. And so we already have our values here. We're going to add a 22.94 plus a 1.39 for the horizontal component. And then we're going to have negative 32.77 plus 7.88 for the vertical component. If we add those together, we'll get the vector v plus w is equal to 24.33 for the horizontal component, and then a negative 24.89 for the vertical component. And so that's v plus w. That's just combining the velocity of the ship with the velocity of the water. And again, it's going to be because the horizontal part's positive and the vertical part's negative, we're going to be down in the fourth quadrant. Okay. All right, so that's the true velocity. So to find the true speed, remember speed, we've already been treating speed as a magnitude. So I now want to compute the magnitude of this velocity vector. So I want to compute the magnitude of v plus w. And magnitude's pretty easy. We're just going to take the square root of the sum of the component squared. So we're going to have the square root of 24.33 squared plus the negative 24.89 squared. And if we compute that, we will get that our speed is 34.81 miles per hour. So the ship is actually going a little bit slower in reality than what it was sort of originally trying to go. So it was set to travel at 40 miles per hour. But because the water's sort of pushing in the opposite direction, it's pushing to the north, it's going to slow the ship down. So the ship's actually technically only traveling about 34.8 miles per hour. All right, the last piece that we want here is to find the true direction of the heading of the ship. And we want to do that as a heading. So heading just means we want to express it as a north or south, east or west angle using our cardinal directions. Okay. And so we know that to find the angle for a vector, we're going to use the tangent of theta is equal to b over a. And in this case, the b is our vertical component, so that's that negative 24.89, and a is the horizontal component, that's that 24.33. So we're going to have the tangent of theta is going to be a negative 24.89 divided by 24.33. That's obviously not a nice unit circle value, so we're going to have to convert this to an inverse tangent. So we're going to have theta is equal to the inverse tangent of a negative 24.89 over a 24.33. And we'll go ahead and compute this as an angle in degrees. Using our calculator, we get that this angle is a negative 45.65 degrees. Okay, so I need to take that angle, that's a standard position angle, and it's in the fourth quadrant. I need to convert it to a heading angle. Okay, so again, that's a clockwise angle because it's negative, and it's a negative 45.65 degrees. So I could say that my heading is east 45.65 degrees south. So that would be true. But sometimes we like to have the angle written from the north or the south perspective. So if I were to figure out what this angle from the south would be, then we could just subtract that 45.65 from 90, which if you do that, you get 44.35. So I could also say that this heading, the ship is heading in a direction of south 44.35 degrees east. So those are different ways of expressing the same direction. Okay. All right, let's try one more. All right, so this time we have Ted. He's driving home from the local grocery store. He must drive, to get home from the grocery store, he must drive 4 miles due east, then 1 mile due south, and then he has to turn and travel 2 miles southwest to arrive at home. Okay. Well, later that day, he ordered a meal from the same store to be delivered by drone. How far must the drone fly from the store to his house, and at what heading? Okay, so we want to find the distance, total distance, or the direct distance from the store to his house, and then we want to find the heading. And again, heading, we want to think in terms of a north, south, east, or west angle. Okay, so with all these types of problems, let's first draw a picture. All right, so we have our XY axes here, and we're going to say the grocery store is at the origin. That's where Ted starts, and where the drone is also going to start. So Ted must drive 4 miles due east. So we're going to go 4 miles due east. So due east would be to the right. All right, north is up, south is down, and west is to the left. All right, he then drives 1 mile south. So we're going to go 1 mile south. And then he's going to travel 2 miles southwest. So southwest would be kind of down and to the left. And I'm drawing all of these angles, or sorry, all these vectors, because this is the route that Ted has to travel to go from the store to home. We're going to just put one arrow at the end of the previous arrow. So we're just going to chain them together in sequence. Okay. So we're going to go 4 units to the right, 1 unit down, and then 2 units kind of down and to the left. Okay, sort of at a 45-degree angle to the left. Okay, and wherever that point is, that's where our drone is going to have to fly, right? The drone doesn't have to follow the street directions. It can just fly in a straight shot. Okay, so we want to figure out what that is going to be. So to do that, notice that that drone vector, which I'll just call that V here, this vector is really just the sum of the 3 vectors that Ted has to drive. So let's try to figure out what those 3 vectors are that Ted drives, and then add those together. And that will give us the vector for the drone. Okay. So 4 miles due east. So that is a vector where there's 4 miles up to the right. So that's 4, a positive 4 for the horizontal component, and then 0 for the vertical component, right? Because it's 4 to the right, nothing up or down. We then have 1 mile south. Okay, so 1 mile south has a 0 change, 0 distance traveled horizontally, and 1 unit, 1 mile vertically, but we're going to think since it's to the south, it's going to be negative. So we're going to have 0, negative 1. So we have 4, 0 for due east. We have 0, negative 1 for due south. And then we need to figure out the vector for the 2 miles southwest. Okay, so to do that, remember that southwest. Again, southwest would be an angle into the 4th quadrant, and we're just going to say it's like right in the middle. Southwest is 45 degrees, but I have to have the standard position angle. So that's 180 degrees to go from x-axis across through the 1st and 2nd quadrants, and then an extra 45 degrees into the 3rd. So 180 degrees to track through the 1st and 2nd quadrant, plus the 45 degrees into the 3rd quadrant. And so 180 plus 45 is going to be 225 degrees. So this 2 miles southwest, that vector is going to look like 2 times the cosine of 225 and 2 times the sine of 225 degrees. So again, if we add those 3 vectors together, we will get the vector that represents the direction that the drone must fly. So if we add those 3 together, we will get the velocity vector for our drone. And we can go ahead and use technology to do that. So if we add the horizontal components, that's the 4 plus 0 plus 2 cosine of 225. That will give us 2.59 for the horizontal component. And then if we add 0, a negative 1, and a 2 sine of 225 degrees, that will give us negative 2.41 for the vertical component. So that is the vector of the drone. Okay, because it is the result of adding together the 3 vectors that Ted has to travel. Okay, so now we need to figure out how far that is and the heading. So the distance, how far it is, that's just going to be the magnitude of our vector. So if we want to look at how far, we're just trying to compute the magnitude of our vector. Okay, and remember, magnitudes of vectors, you just take the square root of the components, the sum of the components squared. So it's the square root of 2.59 squared plus a negative 2.41 squared. And using a calculator, we get that that's going to be 3.54 miles. So the drone does not have to travel the 4 miles plus the 1 mile plus the 2 miles. It's not going to travel a total of 7 miles. It's just going to travel a direct line from the store to Ted's house, and that's only 3.54 miles. And then if we want the heading, so again, heading that deals with angle. So to find angles, we're going to look at the tangent of theta, and it's equal to the vertical component over the horizontal. So tangent of theta is going to equal a negative 2.41 divided by 2.59. We're going to have to go ahead and do our inverse tangent for that. So theta is going to be the inverse tangent of a negative 2.41 over 2.59. And if we use our calculator, we will get a negative 43.03 degrees. Again, that's a vector that's an angle in the fourth quadrant, and since it's negative, it is rotating clockwise. Okay, and that should make sense. If you look at the vector for the drone, it has a positive horizontal component and a negative vertical component. So it is a vector pointing in the fourth quadrant. We just want to express this again as a heading, not an angle in standard position. So to convert this to a heading, we could say the vector has to travel east 43.03 degrees south. Or if we wanted to combine that with 90, so 90 minus that 43.03, we would get south 46.97 degrees east. So either of those would be acceptable